Hello, this is Team MRI Mavericks from University of Babes-Bolyiai, comprised of Tudor Mihaita, Alex Profir, Mihaita Lacusteanu and Claudiu Petrila. My name is Tudor and today I will guide you through a quick overview of our project done for the Artificial Intelligence course, titled Medical Imaging Reconstruction Techniques. First and foremost, it will be important to understand the problem we dealt with and the adopted perspective in order to find a solution. Therefore, we have to talk about uterine cervical cancer, one of the most common forms of cancer found within a very high number of women. This cancer typically develops slowly over time, starting as abnormal changes in the cells of the cervix and eventually leading to invaded tissues or organs with potential tumors growing inside the body. Because of this, medical imaging has a very important role when it comes to diagnosing patients in the early stages. It is also very useful for treatment planning and monitoring the progress of the disease, which can be easily recognized by a doctor just by analyzing the patient's scans. Here is how these images would look like in a raw, unfiltered, and unprocessed format. Pretty hard to spot potential anomalies, right? Having this in mind, we thought it would be a great idea to look into a possible use of artificial intelligence in this field of medical treatment. And of course, we found many different benefits it brings to the table, ranging from the possibility of predicted patient responses to certain treatments to even detecting genetic predispositions to specific conditions. More than that, AI also provides an impressive amount of complex medical imaging processing techniques with a focus on reconstructors. Basically, reconstructors prove to be extremely useful for exposing features in an MRI or CT scan, which can give a very specific idea of the current state of a patient and his reaction to a disease. Here's another example of how such scans look after a bit of processing and the amount of information they provide if correctly interpreted. With all this information, we went hard at work to implement our own machine learning model centered on the task of reconstructing MRI and CT scans with possible enhancements. In the following slides, we will take a closer look at the steps we went through for implementing the model. And of course, we have to start with data gathering and pre-processing. Therefore, we opted for using an open source, anonymized dataset with both MRIs and CTs for each patient undergoing treatment for uterine cancer. All this collected raw data has further been pre-processed using a special pipeline which applies operations such as resampling and registration, resulting in an output format much easier to analyze. As you can see, when putting everything together and applying a special color encoding, data seems clearer, but still, reconstruction should give the possibility of extracting even more information for correctly identifying the anomalies in the tissues. Once everything was set up, we had to decide on the implementation of the model, and the first concept that came to mind was the encoder-decoder architecture. To simply explain how this works, let's imagine taking a piece of paper, crumpling it in a tiny ball, and then unfolding it back to its original dimensions. This is exactly how an autoencoder works, a model made up of two components. An encoder, which downsamples an original image to a compressed representation with reduced sizing, and the decoder, which puts back together an image very similar to the original one, given as input the compressed image this time. This architecture has proven to be very effective when it comes to reconstructing MRIs or CTs. However, we still kind of wanted more from our model, so we went further with trying another approach as well. This one is called a generative adversarial network, or for short, a GAN, which also has two key components, a generator and a discriminator. And again, in order to explain this concept easier, let's make another analogy. This time, we will represent the generator as a criminal and the discriminator as a police officer. The criminal is generating fake dollar bills based on the real ones provided by the bank and is trying to trick the police officer into believing that his fake money is also real. This type of behavior of the GAN architecture seemed to be exactly what we needed for improving the reconstruction model. So, for our task, we assigned the autoencoder done in the previous iteration as the generator part and added another artificial neural network as the discriminator as well, which help improve the generated MRI and CT scans based on the additional training provided when attempting to fool our police officer. This has led to some quite impressive results, we believe, with an emphasis on the reconstruction accuracy, which was successful in both scenarios we tested. Detection of the affected tissue should also be greatly optimized by using the reconstructed scans, but only through enough training so we would minimize the loss of information when upsampling the images back to their original dimensions. Here are a few examples of the generated outputs, the progress done through the training process, and the comparison with the original data to demonstrate the actual utility of the model for this problem. We also believe we can bring some feature improvements to our project. Having a more varied dataset will give better results in most scenarios of training a machine learning model. Also, overfitting prevention should be taken into consideration, which basically refers to creating a model that produces perfect results on the training dataset but performs poorly when used in real-world data. More than that, continuing with the task of cancer localization should be the goal of the following iterations. To wrap this up, this was the project presentation for Team MRI Mavericks. I hope you find this solution interesting or at least inspiring for other future implementations. We hope you're having a productive day and thank you for your attention.